Higher order derivatives. So after taking the derivative once, if you wanted, you could take the derivative of the derivative. And that would be the second derivative. And then you could take the derivative of the derivative of the derivative. And that would be the third derivative. Well, we're going to find out, okay, we're going to find out in our next unit, applications of derivatives, where why would you want to take the derivative to begin with? Well, taking the derivative to begin with can really help you find maximum and minimum points, because if the slope of the derivative is 0, that means that your tangent line has a slope of 0, and that can only happen at maximum and minimum points. What the second derivative is going to help us find is this point. What is that point? That's the point on that graph where it changes from being concave down to concave up. And as another aspect of graphing, it doesn't look that way. Can you see that this section here before, the curve is all down, and after that point, the curve is all up. So as far as a graphing thing goes, our second derivative tells us where that changes. We're going to find out in other applications that the derivative of distance is velocity, and the second derivative, or the derivative of velocity, is acceleration. So we're going to be able to use some kinematics and do some physics stuff and find out how the derivatives relate to that. But then once you find out that you can do a second derivative, you could just keep going, right? Because it's just taking the derivative of a new function. So for example, I'll give you, all right, if y is equal to e to the x, I would like you to find this derivative. It's still e to the x. Okay, good. Excellent. It wouldn't be too bad. Of course, if we had a chain rule in there, then things might get a little bit different. But let's not yet. So we learned some new notation. We can just do the double prime with the f of x or with the y. Or in Leibniz notation, we can square the top and square the bottom, but where we put those squares, the square is in between the d and the y on the top, and on the bottom it's the whole thing squared. Now, part of that might come from, you remember this notation when it says take the derivative of something? And this would be, right? This basically is your y, right? And this is dy dx. If you had the derivative a second time, you would have the top twice. That's why it's d2y. The d squared happens between the d and the y. And the bottom happens twice, but they don't actually put brackets on the bottom. But I think that's where it comes from. But you don't care where it comes from. You just go, okay, that's new notation. There it is. The questions aren't hard, but you just have to do the derivative twice. Sometimes that'll mean that a product rule or a chain rule will appear after doing something first. So try this. Could you find the first derivative? And then if you find the first derivative, could you take the derivative again? And what would you get? And sometimes you'll want to simplify part of the way in between, just because it makes taking the derivative again easier. So there's our first derivative. Did you change the x to a minus 1? Probably makes sense more to do that than it would be to use the quotient rule. And then take the derivative again. No problem. Same kind of question, just using different terminology. Before we do this, what kind of rule is going to happen when we do our first derivative? Product rule, quotient rule, chain rule. It's going to have a chain rule. And then, after the chain rule, what's going to happen in the second derivative? It'll have a product rule. So I don't know if the blue boxes are any kind of indication of whether it gets shorter or longer by the end, but it appears that it might be a pretty long second derivative once we're done. So there's our first derivative with the chain rule. If you simplified things a bit, so what I've done is I've multiplied that 3 by the 2x minus 3 to make 6x minus 9. Then I have a product rule with a chain rule afterwards. So I keep the first the same, derivative of the second, which is our chain rule, and then kept the second the same, derivative of the first. In this case, you might start to wonder, maybe it would have made sense to actually expand the top completely and multiply x squared minus 3x times x squared minus 3x times x squared minus 3x. Because then my function will be really easy to take the derivative of, and then the second derivative and the third derivative, and so on. We got our chain rule to begin with, and then chain rule again, and it keeps flip-flopping between sine and cos and sine and cos. So what happens on your final exam? They might say, what is the formula for the nth derivative? What do we notice as a pattern? Could we do that? Could we do the nth derivative of x? Well, yes and no. Because depending on what n is, it's going to flip-flop between sine and cos, sine and cos, sine and cos, sine and cos, sine and cos. But they might say the nth derivative has the form something sine 2x with something in front. Suppose n is an even number. Can you see that if n is an even number, it'll always have sine. If n is an odd number, it'll always have cos. And the question they have for you is what goes in front here? Can you see that by the nth derivative, this eventually will disappear? The 12x squared, next time it's going to be 24x. And after 24x, it's going to be 24. And after that, it's going to be 0. And then it's going to go away. But what's happening to our coefficients? It started with 1 here. Now it's a 2. Now it's a positive 4. Next, it's going to be negative 8. Right? And then it's going to be, it's going to flip-flop from positive, oh, actually next it's going to be 8, and then it's going to be negative 16, and then flip-flops back and forth there. And then they might want you to notice, what are those numbers, 2, 4, 8, 16? That makes a geometric sequence. So they start off with a derivative question, and in the middle of a derivative question, they get you to change to a whole different unit. You will see that on your exam. You'll see that in some of your questions. You've seen it already, maybe in some of the lab stuff. But they like to say, how could we write a geometric sequence question inside a derivatives question? So your mind has to be ready to switch back and forth. Anyways. Have you done this one already? You want to see the answer? Not yet? Okay. First derivative. And then if you leave it like this, then it's a quotient rule for your second derivative. You could have also brought that x squared plus 1 and made it to the negative 1, and then you'd have product rule with the chain rule for your second derivative. So here we have product rule and chain rule. And what I've done in the second step there is I noticed there was an e to the 2x in both of those terms, so I factored it out. But you could have left it as the first part again. But when I factored it out, do you see that going to the next step, this is going to be a product rule again? Without it factored out, there's still a product rule in the first part, plus there's another derivative in the second part. It'll work out the same, and you'll get the same answer. But when you do your second derivative, keep your first function the same, derivative of the second one, plus keep your second one the same, derivative of the first one, and you have another chain rule there. Another chain rule. And then another chain rule when you do your second derivative. So this equation here has a t and an s. This is notation that would normally be used for distance and time. So here's some function with distance and time. And if we find our first derivative, we get negative 32t plus 16. And if we do our second derivative, we get negative 32. Now, we can now test the validity of, does this question actually make sense? And a few things that we would take from this. Do you know what acceleration is of gravity? Okay, what is it? Negative 9.8 meters per second squared. Does anybody know it with other units? Have you ever had to do American textbook questions? Do you ever have it in feet per second squared? No? I believe when it's feet per second squared, it's close to 32. Okay? Because there's about 3 feet in a meter, so you times 9.8 times 3, you're going to get close to that. So this question actually, when you take the second derivative of a distance formula, you should always get gravity. You might have remembered, well, no, you don't remember. But I'll tell you that when you were in grade 10 or grade 11, learning quadratics, sometimes they gave you height questions. And when they gave you height questions in your textbook, there might have been a few, if they were the graphing calculator ones, that would have started off with a negative 4.9 t squared, maybe plus 10t minus 5, or probably plus 5, projectile off a cliff or something. And this would have been the equation. Look at the first derivative, negative 9.8t plus 10. Look at your second derivative, negative 9.8. So you could test the validity of those questions if they were realistic. And when I look at them, I'll notice that, oh, when they want you to use your calculator, they'll have negative 4.9 because they want to be accurate. But when they had questions that they wanted nice to factor, they started off with a negative 5 because it's close enough. But then that would mean acceleration on that planet was minus 10 meters per second squared. The other neat thing about these equations, and we're going to learn more about this in our applications unit, is if this is our distance or our height, this becomes our velocity, this becomes our acceleration. Well, acceleration is a constant, but our velocity could change. In fact, if you throw something up in the air, eventually it stops and then starts coming back down. But the nice thing about your regular quadratic is this second number, if you plug in 0 for t in your velocity equation, that second number is always your initial velocity. So now when you look at parabola questions, you can look at them differently. There's a lot of information there. They're telling you about gravity. They're telling you that in our question here with the 16, this one had an initial velocity of 16 feet per second. And what would that mean if that thing was thrown up in the air? Anyway, so there's some really cool kinematics applications that we're going to get to in our next unit as well. Final question here. Take our first derivative. It's a chain rule. Simplify it a little bit so we get 8e to the 2x. Take our second derivative, another chain rule. Get 16e to the 2x. Plug in 1. And if we want 3 sig figs, it's approximately 118. So second derivatives, not super hard. Just means that you have to know how to do the derivatives more than once. Sometimes a little simplifying in between is helpful. We saw in that one question that I did with the quotient rule before. Some of you did it with the product rule. So you have some options depending on how you look at it. And that is the end of our derivatives unit.